So free body diagram. What kind of loads do you have at the wall? At that pin joint?
Full force.
Yep, force vector. So I'll call that force on the body by the wall, and no couple. And then we know that there's a tension. So I draw the arrow, and that's a scalar variable then. And what's the force vector applied by that distributed load?
500 newtons right in the middle.
500 newtons, and right at the centroid of that rectangular shape, so right in the middle. And then the force due to the weight of this object is 50 times 9.81, so 490.5, and it's acting a third of the way from this end, right? So so we have 490.5, and this distance is a sixth of a meter, right? What's that? 0.166 is?
No, it's two. It's 2/6. It's 1/3 of a meter.
This is half a meter.
Yeah, it's 1/3 from that side, so
Oh.
it's 2/3 from that
Right,
side.
right. I
which
was,
is
yeah.
0.333.
That's right. Yep. A third of the way from this side. A third of the,
2/3 from that side.
right. A third of a meter from
Third of
this
a meter.
side. Yes. Okay. Okay, because the, okay. Okay, yeah, because, I mean, that's from the rectangular distributed load.
We'll see. I don't know.
So prepubescent athletes, row for mommy.
Solving this problem as an engineer when I'm like 60, and I'll remember that.
That's good. That's the goal. So actually, since all these forces are up and down, writing out this table is a little bit of a slower way to go, but that's not a big problem, you know, like, I don't think this is a bad way to go ever, you know. You're never going to have to like race to finish exams in this class anyways. So let's put the origin here. And let's put the about point there too. So first, that force at the pin joint acts at 0, 0. The about point is 0, 0. So rho is 0, 0. Then we have force on the body by the wall, x and y. And so the moment is 0. Then we have the force due to the distributed load. Where's that acting? 0.25. And then any y location is fine. So 0.25, 0. About point is zeros. So rho is 0.25, 0. The magnitude is 500, so we have 0, negative 500. So we have negative 125.
Yep.
Then the gravity force, I'll put the y location at 0. Since that's vertical, we can move it up and down. The x location is 0.33. about point stays the same. So rho is 0.330. The force is 0, negative 490.5. So what's a third of 490.5? So negative 163.3. And then the last force is that tension force. Did anyone get something different? Is that right?
Well, it's just 0.5, I think. 163.5.
Okay.
490.5 divided by 3.
Oh, I did 0.33 times.
Okay. So yeah, we're getting a little round off there. And then that tension force, that's acting at 0.5. Again, we can move the y around. I'll put it at 0. So we have 0.5, 0. The force is 0, positive t. So this is 0.5 t. So Newton's second law says the forces on the body due to the wall plus 0, negative 500 plus 0, negative 490.5 plus 0t equals zeros. In the rotational version, negative 125 minus 163.5 plus 0.5 t is equal to 0. So t is 288.5 times 2. 5. What is it?
577.
Okay. And then what's the force vector at the wall?
0, 416.5.
Other people got the same things from those? Okay. So that's really like, as far as the complexity of these kind of problems, that has the most thrown at you that you can have. You can make the individual parts, individually more difficult. You can make this a shape that you have to integrate and make this a shape you have to integrate. But all you're doing is doing these piece by piece, adding the pieces together the way we did here. So I would recommend, like, just don't lose sight of the sort of simplicity of what you're trying to do. Like, the big picture is simple. It's only the pieces that you can make more complicated than this. Okay? Any questions about this? Okay. So now, the next topic is, to me, like the real heart of this class. Like, I would guess if you asked like a group of people who teach this class to give one problem that they think somebody who's taken statics should be able to do. Almost everybody would give a structures problem, okay? So structures are collections of rigid bodies connected by joints. And the goal is always the same. We want to calculate the loads applied to each body at the joints. So an example of this kind of problem, one example would be like this. Where all these are pin joints. That's sort of a common type of problem. And you want to figure out on each of these bodies what are the external loads, okay? And this might be sort of a dumb example, but you also, this approach is used in biomechanics all the time. So the first thing that came to me was maybe you want to calculate like what the forces are in the trapezius muscles in a gymnast doing an iron cross. Okay, so you'd model it something like this. The rings are applying a force here that's going to be equal to half the weight each. Okay, and those pin joints obviously aren't going to support that position. So what's happening to make that person stay like that? There's a set of muscles that you can treat as cables going from, you know, just a little ways into the arm, connecting to the ribs somewhere, okay? And those cables, if you put a high enough tension in them, can counteract this huge lever arm advantage that the rings have, okay? And it looks really hard. So we'll do a few examples that are biomechanics problems like that of different types. You know, you can calculate what kind of muscle forces you have to put your body in different configurations. So I want to start with by just sort of common sensing our way through a simple version of a problem like this. And then what we learned from just kind of going for it, we'll put into like a set of steps that you can take to the bank on all these problems, okay? So let me just write the problem out and we'll start it next time. So we're going to do a problem where you have a pin joint connected to one member another pin joint connected to the other one. They're connected by a pin joint. And there's a force applied at this pin of 500 newtons. And we know these distances. We'll call this an equilateral triangle with lengths of 1 meter each. Okay. And basically the way we're going to do it is we're going to start by isolating the whole thing, but that won't be enough. What we'll see is that when we isolate this whole body, you won't always get this, but if we isolate these two members as a single thing, we'll end up with 4 unknowns, because we have an unknown force vector here and an unknown force vector here, but only 3 equations, obviously, because we only get 3 from a single rigid body. And then we're going to just sort of go on isolating individual bodies until our number of equations catch up with our variables. Okay? And at each step, we're just, the body that we isolate, we're going to do what we've been doing. We're going to use the joint type to figure out what kind of loads are applied. And then we're going to draw a free body diagram and use Newton's laws. Okay, so from that, we're going to move on to how to approach these problems in general next time. Okay, so all right, see you Thursday.